but it's really ultimately limit problems. So we're going to look at the first two today, the main two, and then on Friday, you guys are going to watch videos on the other 5 ones. Okay, so the goal is always to be able to rewrite things so that it's in these first 2 original indeterminate forms. So what I mean by indeterminate is anytime you guys do a limit problem, your first step should be plug in, do direct substitution. And what do you get when you do your initial plug-in? And what we end up with is something that is indeterminate, 0 over 0, or plus or minus infinity over plus or minus infinity. Okay, so I'm going to prove it to you guys first. If the proof is like, if that goes over your head, that's fine. It's okay. I just want to make sure you guys see it. You're not responsible for proving this. You're just responsible for applying it. So here goes the proof. Okay, so you guys have a rational function. Let's call that rational function f of x. Okay, that it's a ratio of h of x over g of x. Okay, so right now all we know is that f of x, which is what we're trying to find the limit of, is the ratio of 2 functions. And we're going to let a few things be true. Let's say we're going to let, and this is the part where if you were doing your initial plug-in, if you were doing direct substitution, and let's say you were asked to find the limit as x approaches a of f of x, of this function. Okay, so ask yourself what you would do. You would plug in a into the top function and then a into the bottom function. So h of a and g of a. Okay, that's your direct substitution part. And in doing so, you discover that you get an indeterminate form. You get 0 over 0. So let's say limit as x approaches a of h of x happens to be equal to 0, and so does g of x. Okay, you do your initial plug-in, you do your direct substitution for the limit problem, and you guys can say initial plug-in. Okay, in evaluating the limit, you discover you have an indeterminate form. Okay, you also happen to know that h of x and g of x are differentiable functions. Okay, you can take the derivative does exist. Okay, in the chat, as soon as you guys write that out, h of x and g of x is differentiable. What else can you guys conclude? So if h and g are differentiable, what can you guys conclude about h and g? You should kind of flow from how many times we've discussed this before. Very good. Okay, so if we know it's differentiable, it's only differentiable if the functions are continuous. Very good. So also continuous. So this part might be a little bit harder for you guys to remember. Back in chapter 1, when we talked about continuity, there was like 3 hurdles. Remember, the limit had to exist. The function value had to exist, so there can't be a hole there. So again, the 3 hurdles were the limit has to exist, the function value has to exist, and the last one was that whatever the limit was had to be equal to the function value. So we will say that as, if it is continuous, the limit as x approaches a, both of h and of g, but I'll just say it of h for now. If they're both differentiable, this has to be true for both functions. The limit as x approaches a of h of x, or in other words, the limit must be equal to the function value, so that we ensure there's no hole and that the limit does exist on both sides. Okay, so kind of a roundabout way, but if we look back at what we established at the beginning, when we did our initial plug-in, the limit as x approaches a of h of x was 0. Okay, so we can say all of that is true, and we can assume that all of this is 0. Okay, so let's set up our problem. So our initial problem was limit as x approaches a. So all of that is given to us. All of those are assumptions. Sorry, lights went off. Limit as x approaches a of f of x. That's going to be annoying. Sorry. So limit as x approaches a of f of x means that I'm plugging the limit, the value of a into both the top and into the bottom. So limit as x approaches a of h of x and of g of x. Okay, so that's the direct substitution part. Okay, here's now the algebraic manipulations I'm going to do. Okay, if I know that this is true, if I know that h of a is equal to 0, if I subtract 0 from something, it doesn't really change anything. So what I'm going to do is on top, I'm going to subtract h of a. And the same assumption can be made about g since it is differentiable. I'm going to subtract g of a as well. So essentially, I have not changed my function at all, right, by subtracting h of a and subtracting g of a, because essentially those are values of 0. Okay, and then let me know if you guys start to spot what we're doing here. And then if I decide then that I want to multiply the top by 1 over x minus a, I would do the same thing on the bottom, and still, again, multiplying by 1 over x minus a will not change my fraction in any way. Does anyone want to type into the chat? Go ahead and type in the chat if you guys start to recognize something that comes from what I just did, the expression on top and bottom. Any guesses? And maybe I rewrite it. So limit as x approaches a. Yes, and then someone said what you do on the top versus the bottom, that is true. What you do to the top, you do to the bottom. Does anyone recognize that? Think of the Jeopardy game that we played. Okay, so I have Tim guessed it correctly. Okay, very good. Tiffany, Heather, that is correct, you guys. That this is the second definition of the derivative, or a second form of the definition of derivative, similar to f of x plus h minus f of x all over h, where you let the limit of h approach 0. This is the second definition of the derivative. So all of that is the same thing as me just saying the limit as x approaches a of h prime of a over g prime of a. And so I'll box it over on the right. But these two are mathematically equivalent to each other. Okay, so our initial problem was, what was the limit as x approaches a of f of x? And f of x, remember at the beginning, was h of x over g of x. So this is the rule that we're going to apply when we do have indeterminate forms of 0 over 0 or infinity over infinity. Okay, so that was the proof of it. And now we're gonna do the simple application of it. So you guys will like these problems tonight. They're pretty simple. You're just taking derivatives and evaluating. The hard part really is just remembering all your derivatives. Hopefully not a difficult task because you studied for your final. Okay, so for our first example, these problems look exactly like the problems you guys saw in first semester in chapter 1. Now you guys have a nice, easy shortcut to do, to use for these. I think this one you guys could have done using a trig identity. But when we do our initial plugin, so this is going to be where I'm going to emphasize, please make sure you guys always do direct substitution first to see what you get. It has to be indeterminate for you guys to be able to apply L'Hopital's rule. So in the chat, can you guys tell me, what do you guys get in the initial plugin? What do you guys get for this limit? Okay, so good. You plug in 0 on the top and 0 on the bottom, and you guys get 0 over 0. So I'll always write out that in pink. It's not necessary. I think someone asked me yesterday, do we have to write that on the AP test, the 0 over 0? You don't. I do that in my notes because I want you guys to remember that you're supposed to do that every single time you do an iteration of L'Hopital's rule, because we'll see that you can apply this multiple times. So in determining that it is 0 over 0, after that we apply it, which is simply take the derivative of the top and put it over the derivative of the bottom, and then do your direct substitution. It is not quotient rule, because I've had kids mistakenly believe it's quotient rule all the way to the chapter test. It's different from quotient rule because you're just treating the top separately from the bottom. Okay, so if we take the derivative of the top, you guys get sine of x. If you take the derivative of the bottom, you get 1 plus 2x. and every time you take the derivative of the top and bottom, do the plug-in again. Can you guys type into the chat, what do you guys get when you do the plug-in again? Okay, and you would stop, you would know you can stop with L'Hopital's rule when you get a finite answer. And in this case, when you plug it in, you get 0/1, which reduces to just 0. So that tells me that this limit is just 0. Okay, not that it's like an indeterminate form where we keep going, because that's the mistake. Sometimes we just reapply again without thinking about or without doing that direct substitution to determine it's not indeterminate. So make sure you guys are plugging in along the way. So example 2. Limit as x approaches 0 of e to the x minus 1 all over cosine of x minus 1. Okay, take a moment and type into the chat, what do you guys get when you do your initial plug-in for this? Okay, good. Yeah, I've made a mental note that when I plugged it in, I get 0/0, so good. And then from there, apply L'Hopital's rule. So go ahead and take the derivative of the top and the bottom, see what you guys get. Actually perform the first iteration. Go ahead and do the derivative and then tell me what you guys get. Oh, sorry. Don't tell me what the derivative is. Tell me what happens when you plug it in. Okay, 0/0 again. And so it works, L'Hopital's rule works multiple times. So that was the first iteration. Go ahead and do the second one as well. So go ahead and try it again. And then type into the chat, what do you guys get? Okay, and our loop ended, right? So right after we plug in, after this iteration, we get good. -1 is the conclusion you guys make for this limit. Okay, and then as the last L'Hopital's rule example, I'm going to say for example 3, can you guys tell me what happens when you do this limit problem? So limit as x approaches 1 of x squared plus 1 over 2x plus 1. So tell me what happens when you guys do this problem. Okay, so recognizing that direct substitution is the first step that we do. When we plug in, we don't get an indeterminate form. So we're not going to mindlessly just apply L'Hopital's rule. Even if it looks like it might be one, make sure you guys do direct substitution first. Double check to see if you guys have an finite value for an answer. And if you do, then that's your answer. It's not like I look at a limit problem and then just automatically start applying L'Hopital's rule. Okay, so the last portion of the notes is going to be on something that should be familiar to you guys already, but I'm going to tie it in with the current unit that we're on because it's going to become important as we move on to the series chapter and the tail end of this chapter. And this is relative rates of growth. And if that doesn't sound familiar to you guys, it will start to sound familiar once I talk about it. But you're basically comparing the rate of growth of two different functions. So for example, just conceptually, if you think of about y equals e to the x versus, so that blue function versus, let's say, y equals x. If I asked you guys to look at values out at infinity, at x equals infinity, which one would you guys say grows faster? Y equals e to the x or y equals x? At values, at large values of x. Okay, intuitively, I think we all can see that and recognize that e to the x will, the growth of e to the x will outstrip that of any really polynomial function, but definitely of y equals e to the x, or sorry, of y equals x. And so relative rates of growth is just like, what is the growth rate of one function compared to the other? And so we're going to tie this in with limits and tie it in with L'Hopital's rule. So the first thing we'll discuss is, let's say you guys have two functions, f of x and g of x, and you make a comparison of one function over the other. You guys gave me the intuitive response, but I want to have you guys write it out in terms of a limit. Okay, so if we have the understanding that f grows faster than g as x goes to infinity, then two things become true. Okay, so let's say that you make the comparison. So I see Kathy and Min responded, so I'll use them as an example. Let's say Kathy says that she's going to compare f to g, and so she's going to say, I want to see what happens to the comparison when I let x go to infinity. If I put f of x over g of x, comparison is a ratio. So let x go to infinity of f of x over g of x. And she gets an answer for it. That leads her to conclude that f grows faster. What would that answer be? If f of x grows faster than g of x, what is the limit as x approaches infinity? What answer would you guys get if f of x or the top grows faster than the bottom? Do you guys remember? Yeah, if your top function grows faster than your bottom, that means you have a bigger top. So very good. We would make the conclusion that the top grows faster if infinity was my answer. Let's say Min, though, decided when he was going to make the comparison that he was going to put g of x on top and f of x on the bottom. And again, this part of it, if it's not stated to you guys and you're just comparing or making a comparison, you choose f of x or g of x. What would Min get if f grows faster? What would you get as your limit then? What would your answer be? Okay, so a bigger bottom means that you guys are thinking of like this fractional value to be like 1 over a million. And the smaller that fraction, the closer it is to 0. Okay, so those are the two results. If f grows faster than g or g grows faster than f would be the reverse of that. But what if you guys compared the two and you got that f and g grew at the same rates? So if f and g grows at same rate as x goes to infinity, we get a different answer. Okay, so what is it that I get? And this one was, let's see how much of this one you guys remember. What happens when you let x go to infinity if f and g grow at the same rate? What would your limit be? Okay, good. Some people think of the very specific case where you get 1. Someone said a, someone said a finite value. Very good. And then some of you guys are writing what I would think of, which is the ratio of coefficients. Very nice. Okay, so L, and then I'll circle that, and L represents the limit, but it's the ratio of leading coefficients. So sometimes it's 1. So that's what some of you guys wrote out. That's a specific case where your coefficients have a ratio of 1 over 1. But if they are growing at the same top and the bottom, the same rate, you kind of think of it as they cancel out, and you just look at the ratio of the leading coefficients. So yeah, it might seem very familiar to you guys as you studied for your final, that you were studying this in chapter 1. My other question to you guys is, graphically, what does this represent? What does this L value represent on the graph? If you're looking at things as it goes out to infinity, what does that constant represent? Very nice, you guys. It represents your horizontal asymptote. Very good. So horizontal asymptote. So also that's how you guys would find horizontal asymptotes, is just putting a ratio of one over the other, or looking at your function and then finding that ratio. If it does exist as a constant value, that represents your horizontal asymptote. Okay, so in the last few examples here, last two, I'm just gonna have you guys tell me which one grows faster, or do they grow at the same rate? Okay, so which function grows faster? And same rate is an option. Okay, so one of them I should have called it g of x, but oh well. I have y there is equal to 3x squared plus 4x cubed plus 100x to the fourth. And then f of x is 1/2 x to the fourth minus 2x squared plus 4x. Okay, can I have you guys go ahead and set up your limits and make a determination? Which one grows faster, or do they grow at the same rates? Okay, so you guys are typing in that they grow at the same rate, which is correct. I think I had a couple people yesterday say that that y was growing faster, that the top was growing faster, and so we want to be careful because I think that person was just looking at the 100 and thinking, okay, that one has to grow faster for sure. We remember we look at this in terms of infinity, what's happening when we get really large for x. And so when you guys make a comparison, by the way, I'll circle it and just kind of like cross it off on your ratio. These are what we call negligible as we go out to infinity. They're not going to control what happens. So kind of like think of that as they drop away, and you're really just comparing 100x to the fourth over 1/2 x to the fourth. So you get a value, and even though that value seems large, it's still just a constant. So that's why you end up with just 200 as your, oh, you know what, actually, Min, I'm gonna come back to that. So Min, when he did his initial plugin, he got infinity over infinity and took derivatives. That's actually correct as well. So I think you can think of it conceptually like I just did here. And then I'm going to force you guys to do the L'Hopital's rule on the second example just to verify that is true. I didn't want you guys to do it for this one just because it might take a little while longer, but you should get the same results. It should reduce down to a constant, so they grow at the same rate. And that's why I put that in this section. Actually, the whole L'Hopital's rule part does apply, and you guys might not know, but you're informally doing it in your head. So let's say example number 2. You have same question. You're comparing y equals e to the 2x and y equals x cubed. Okay, so let's say that those two functions, they ask you guys to make a comparison. And so you're looking at what happens when we go out to infinity. We're going to put one function over the other function. And I want you guys to look at this. I know you already know the answer. So you can look at it conceptually like that, but I want you guys to break it down using L'Hopital's rule. So when I do my initial plugin, when you guys do your initial plugging in of infinity, what do you guys get? What over what? Remember, you guys are plugging in infinity this time, remember, not 0. Yeah, so yeah, we're looking at what happens at infinity, not at 0. So when we do our initial plugin, I didn't do an example of infinity over infinity, but that is also an indeterminate form. So either 0 over 0 or any kind of plus minus infinity over plus minus infinity. Those are indeterminate. So at this point, you guys would apply L'Hopital's rule. And let's say you guys apply L'Hopital's rule, take the derivative of the top. We get 2e to the 2x. The derivative of e is itself, and then the derivative of the baby function would be 2 over 3x squared. Okay, humor me again, you guys. If you plugged in, did direct substitution again, what would you guys get? At this stage, you guys would get still infinity over infinity, still infinity over infinity. If we didn't do any simplification or overthinking of things, it's still infinity over infinity. So that means that we would continue with our iterations of L'Hopital's rule. We would get 4e to the 2x, chain rule on that, 6x. Again, if you guys do plug in, what do you guys get? Yes, so far we're still getting infinity over infinity. The question is this ever going to end? So let's say you guys go on this next one and you get 8e to the 2x over 6. Do your plug-in at this point? What happens? Okay, and notice the subtle difference between the answer that you guys got at that stage versus the previous stage. At this stage, now it becomes apparent that you have infinity divided by a constant 6. So our answer for this one is infinity. And so it ends at that point when the L'Hopital's rule ends, when you guys get a definitive answer. In this case, it's infinity. And our conclusion, remember all of this was to conclude that the top grows faster. So y equals e to the 2x grows faster. Okay, and part of this is going to come into play for our series chapter, and then at the tail end of this chapter, we're going to dig more into that.